We're going to run through this problem, a distillation column problem, where we have an equal molar liquid mixture of benzene and toluene. Okay, so B is benzene, and then T is toluene. Okay, so equal molar meaning the mole fraction of both of those is 0.5. And here's a flow chart. This is, as it says in the problem, a little bit oversimplified description of what actually happens in this process. We're going to do our problem with this one, just doing the analysis on the simplified column. So inside the column, let's go down here. Inside the column, a liquid stream flows downward. Okay, so our liquid is going to flow down, and the vapor stream is going to rise. Okay, so liquid coming down the column and vapor stream going up the column. At each point in the column, some of the liquid vaporizes and some of the vapor condenses. The vapor leaving the top of the column, which contains 97 mole percent benzene. Okay, so coming out of the top, okay, so this is going to be, let's see, Y. I'm gonna label this these different streams here. So I'm going to say this is stream 2. This is going to be stream 3. And then let's label this one stream 4 and stream 5. And then let's do stream 6 down here. Okay, so we have, and then also we'll find that this stream is equal to this stream over here in our problem description. But the mole fraction of benzene in our third stream is going to be 0.97. So therefore we know that the mole fraction of toluene in that same stream is 0.03, and that is going to be equal to, because it's just splitting this stream into 2, that's also going to be the same composition that's coming back into the column. Okay, so I have 0.97 for both of those. So we've used this information, and it's split into 2 equal fractions. Okay, so one is taken off as product. Okay, so this is going to be the purified product. It came in as equal molar and is coming out very, much more pure in benzene. And then this one is going to be another product. Okay, but this is going to be rich in toluene. And we're actually going to do that calculation there. Okay, and the reflux, okay, so this is called reflux, going back to the column is recycled to the top of the column. The overhead product stream contains 89.2, okay, so 89.2% of the benzene fed to the column. Okay, so this is another relationship that we can write down, but the NB3 divided by NB1 is going to be 0.892. Okay, so we've got that relationship right here. Okay, and the liquid leaving the bottom of the column, okay, so now we're going to go down to the bottom, is fed to a partial reboiler. If it was a full reboiler, then it would vaporize all of the liquid, but it only vaporizes part of it, and of which 45% of it is vaporized. Okay, so that means that we have another relationship here, that N5 divided by N4 is going to be 0.45. Okay, so only 45% of it is vaporized. And the vapor generated in the reboiler, the boil up is recycled to become the rising vapor. Okay, so this is where the vapors is coming from, and the residual reboiler liquid off is taken as the bottom product stream. Okay, so this is our toluene rich stream here coming out the bottom. The composition of the streams leaving the reboiler are governed by this equation. Okay, so this is actually going to be we're going to cover this later in the class, but it's Raoult's law. But this tells you, this is just another equation that tells us how the product, how these two, so the vapor and the liquid, are related. Now in this case, Y is going to be the vapor, and then X is going to be the liquid. And in the past, we've said that X is also a mass fraction, and this is a mole fraction, for Y, but we're not going to do that in this case. These are going to be vapor and liquid mole fractions. Okay, so both of those are mole fractions. Okay, so let's okay, and it just defined that right here. Okay, so we're going to take a basis of 100 moles fed to the column. Now, if this were a continuous column, this would actually be 100 moles per hour, or some other basis that was in a flow rate. If you want to think of it as in terms of a flow rate, a molar flow rate versus a total moles, then you could do that as well. So we're going to draw and label, okay, this flow chart. And for each of the 4 systems, we're going to include overall process, column, condenser, and reboiler. We'll do a degree of freedom analysis and identify a system in which the process analysis might appropriately begin. Okay, one with 0 degrees of freedom. Okay, so let's go ahead and just do this one first. Okay, so we're going to go ahead and let me just keep this in our window. And what we'll do is let's just start with the block. Okay, we're going to call this one a block, and this one is just going to be around the whole unit, okay, where I'm making my dotted line. So anything that comes into or leaves that system, we're just going to write our degree of freedom analysis around that block. Okay, so let's go ahead and write out our unknowns for this. The unknowns that we have, so let's do unknowns. That's going to be just N3. We're going to also have N6 and then YB6. Okay, so YT6, we get that one just from 1 minus YB6. So that one is not really an unknown. Okay, so let's go with so the number of unknowns now. Just write this. That's going to be 3. And then how many balance equations we have? Okay, so I'm just going to put balance equations. Well, we can write either an overall mole balance and 1 species balance, or we can write 2 species balances. So we only have 2 independent equations that we can write for our balance equations. And then other equations, our other equation that we have is that we have this this equation right here, that the overhead product stream contains 89.2% of the benzene fed to the column. Okay, so we actually have one more equation. If we subtract, so if we go unknowns minus equations that we have, that will give us the degrees of freedom. And so we have 0 degrees of freedom. Okay, so might be a good place to start the calculation. Okay, so let's go on to the column. Okay, so I'm going to just do the column now. So the column is a little bit different. That's going to be this line that I'm drawing right here, just around the column itself. Okay, not the condenser or the reboiler. And so for the column, we're going to have N2, N3, and then N4, YB4, and N5. Okay, N5 here, and then YB5. Okay, so we have 6 unknowns. We can write, again, 2 balance equations, and then we have a couple other equations that we could use. Let's see, I guess it's just going to be, in this case, let's see, we're just going to have that N5. Okay, so we have this equation right here, and so maybe just one one other equation. Okay, so in this case we're going to have 3 degrees of freedom for the column. Okay, so let's keep going down then. We had our column. Go ahead and just write a line here as we keep going. And let's go ahead and do our condenser. So this is just the splitter. Okay, this one's going to be pretty straightforward. We know that N2 and N3 are going to be our variables. Okay, so we just have 2 there. Our balance equations, we can only write 1 because we can only have an overall mole balance for that. We have no other equations, so we'll have 1 degree of freedom. Okay. Okay, let's go on down to our next one, and this is going to be our reboiler. Okay, so reboiler is going to have N4, YB4, N5, YB5, N6, and YB6. Okay, so all of those, that's going to give us 6. Okay, and then we have 2 balance equations that we can write around the reboiler. And then we're going to have 2 other equations. So we're going to have this one that we had that gave the relationship between the vapor and the liquid mole fractions. And then we could also use this equation here, the N5, okay, divided by N4. Okay, so that'll give us 2 other equations, and so that gives us 2 degrees of freedom. Okay, now let's go ahead and do our, let's go ahead and come down just a little bit. Now this is going to be the overall process. How many variables and equations and degrees of freedom we have. If we just count up all of the unique unknowns, we're going to have 8 variables here. And then balance equations, we'll have, okay, we're actually going to have 5 balance equations. Okay, if we just sum up those that are the individual units here. Okay, we wouldn't include the one with the block because that includes column and some of these others. So you just do the individual units to come up with your overall number of balance equations. Okay, and then other equations, we're going to have 3 of these. Okay, so we had the 3 other equations that were unique, and so that gives us 0 degrees of freedom overall. Okay, so one of the things that we could do at this point was just take 8 variables and 8 unknowns and just solve a system of equations. The other thing we can do is just start off with the block itself. So let's just go ahead and write out all of these equations that we have, and let's come back here to to B. Write in order the equations you would solve to determine all unknown variables on the flowchart, circling the variable for which you would solve in each equation. And so we're not going to do the calculations in this part, just set up the equations. Okay, so I'm going to come back out here, and okay, so let's go ahead and just work down through on part B then. Okay, so first of all, let's go ahead and just write some of these equations that we were given initially. We had NB3 divided by NB1, and that was going to equal 0.892. And so then we had NB3 equals NB1, which we know from our basis. Okay, so we have our first equation, and we would use that equation to solve for NB3. Okay, so let's go on down to our second one, and this is going to be YB3 equals 0.97, but that also equals NB3 over N3. Okay, so we can rearrange that to get n3 0.97 times nb3. Okay, so we have our next equation, and we're going to solve for n3 with that. Okay, so let's go on down to our third one. Now we have n3 equals 0.5 times n2. Okay, so they split them into two. This is a mass balance on the splitter. Okay, so we're going to use that one to solve for n2. Okay, fourth one, let's do an overall balance on the block. So this is where we come and do, from our degree of freedom analysis, said that we could solve for that one. And so we have n1 equals n3 plus n6. Now, in this case, we're going to solve for n6. We have n1 and n3. Okay, number 5, let's do the benzene balance, okay, on the block as well. Okay, so NB1 equals NB3 plus NB6. Okay, in this case, the thing that we're going to get is, let's see. So, well, actually, from NB6, that's also going to equal. NB6 is. Let's see. We're going to get that from NB6 divided by N6 equals, YB6. Okay, and so this is going to help us calculate this. Okay, we had N6 from here. Okay, and then let's see, YB6. I don't think we have that one yet. Okay, but this is going to allow us to solve, this equation allows us to solve for NB6 because we have NB1 and NB3, okay, from our above equation, so we can get NB6, and then we can get YB6 as well. Okay, let's go on to 6, our sixth equation. And we're going to get Y toluene 6 is going to be 1 minus YB6. Okay, and then also we can get our moles that are coming out there, YT6 times N6. Okay, so we're going to be able to get our toluene and then our moles of toluene coming out the bottom. Okay, let's go on to 7. Let's do an overall balance on the column. In equals out. There's no accumulation in this case. So that's just going to be N1 plus N3 plus N5 equals N2 plus N4. Okay, and then number 8, we're also going to use the relation N5 equals 0.45 times N4. Okay, and then we'll go ahead and substitute that in. Okay, so in this case we want to be able to get N4, but we had N5 and N4, so we need to combine these two equations. We'll just go ahead and substitute this one right here, and then solve for N4 and N5. Okay, so we had N1, N3, and N2, so that allows us to solve for N4 and N5. Okay, let's go on down to 9. We're going to go ahead and back substitute. Actually, I guess this was our back substitution right here. Okay. And then let's go on. Our 9th one is then going to be using the relationship YB5 divided by 1 minus YB5 all over YB6. Okay, divided by 1 minus YB6. And that equals, let's see, let me go back to the column description for that equation. That was equal to 2.25. Okay, 2.25. And so that allows us to solve for YB5. Okay, and then if we want to get NB5, we can get that just by YB5 times N5. Okay, so that gives us our NB5. Okay, so let's go on to 10. So 10, we're going to go ahead and get our toluene mole fraction in that stream. Okay, and then let's do our last one here. Let's do a balance on the reboiler. So I'm just going to do a benzene balance on the reboiler. NB4 equals NB5 plus NB6. And for that one, we're going to use that equation to get NB4. Okay, and then we can also get some of our other equations. YB4 equals NB4 over N4, and then also YT4, 1 minus YB4. Okay, so a lot of equations there, but I think it shows us the path forward. For part C now, let's just go back up to part C. We want to go ahead and calculate the molar amounts of the overhead and bottoms product, the mole fraction of benzene in the bottom product, and the percentage recovery of toluenes in the bottom product. Okay, so let's just go ahead and calculate those. We have all of our equations now. It's just plugging in the numbers and solving. Okay, so I have part C now. So let's go ahead and just calculate these. NB3 is going to equal 45.98 moles. Okay, and then this was 1. We're going to go on to 2 now, and so N3 equals, let's see, this is going to be the 44.6 moles of B divided by 0.97, and that equals 40. Let's see, I did this wrong. Okay, NB3, oh, you know what? I need to back up here just a little bit. NB3 was 0.892 times 50. Okay, just that one calculation, and then we had that's going to equal 44.6 moles of B coming out the top. Okay, and then this is where our 44.6 comes, and divided by 0.97. Okay, so N3 then is equal to 45.98 moles. Okay, for our total molar flow rate coming out. Okay, and then we're going to use relationship 4 there. 100 equals 45.98 plus N6, and so N6 equals 54.02. Okay, so if you're just looking at significant figures, you might just say 54 instead of 54.02. Okay, let's use equation 5 now. Okay, so 50 equals 44.6 plus NB6, and then NB6. Okay, so NB6 then is going to be 5.4 moles of B. Okay, and then YB6 is going to equal 5.4 divided by 54, and that is 0.1. Okay, we're almost done, and then we'll go ahead and use it. The next one, we'll use NT6 plus NB6 equals N6, and then NT6 equals 54 minus 5.4 equals 48.6, and so then a percent recovery in the end is going to be 97%. So 48.6 divided by 50 times 100. Okay, so that concludes this problem, and just remember to start with 0 degrees of freedom and then work on through.